Welcome to the deep dive. Some problems are just, well, too big for one person or even one computer to handle alone.
Right. And that's really where multi-agent systems, or MAS, come into the picture.
Exactly. Think of them as like a team of smart software agents, little independent thinkers almost.
They work together, make their own decisions locally, adapt to what's happening around them.
And collaborate to tackle these really complex challenges. We're seeing them everywhere now, aren't we? Like coordinating robots in warehouses?
Yeah, warehouses, smart city traffic management, power grids, lots of places.
So for this deep dive, we're zooming in on a really core problem for these multi-agent teams.
Which is?
How do they all move around, find their paths, without constantly crashing into each other?
The collision avoidance dance. Especially tricky when things are constantly changing, like in those warehouses you mentioned.
Right. So we'll be digging into the research on multi-agent pathfinding MAPF and looking at a pretty cool system called the Shared Recurrent Memory Transformer, SRMT for short.
And we'll also touch on this challenge called lifelong MABF. It's not just about one trip.
Okay, lifelong MAPF. That sounds persistent. What's the difference there?
Well, standard MAPF is often one shot. Get all agents from their start points to their fixed goals done.
Like planning one big coordinated move.
Exactly. But lifelong is more like the real world, especially in logistics or automation. Agents finish one task, and they immediately get another one.
So they need to keep planning, keep moving indefinitely.
Pretty much. Constantly getting new goals, constantly needing to figure out how to get there without causing chaos. It's a continuous coordination problem.
Okay, that sounds way harder.
It is. And that's where some interesting frameworks come in, like one called Rolling Horizon Collision Resolution, or RHCR.
Rolling Horizon. Okay. And then there's SRMT, which you mentioned uses shared memory. That sounds intriguing.
Yeah, two different angles on tackling this ongoing coordination challenge. RHCR focuses on managing the planning horizon, while SRMT explores how agents might coordinate more implicitly.
All right, let's unpack RHCR first. How does this rolling horizon idea help with the lifelong problem?
So instead of trying to plan everything out forever, which is computationally, well, basically impossible in a dynamic setting.
Makes sense. Things change too fast.
Exactly. RHCR breaks the big lifelong problem down into smaller, manageable chunks. They call these windowed MAPF instances.
Windowed MAPF, like looking through a smaller window into the future.
That's a great way to put it. There's a bounded time horizon. Let's call it W. It's a specific number of future top steps.
Okay.
Within that window W, the system focuses only on resolving potential collisions.
Just for that short period.
Right. And there's also a replanning period, H, which is usually the same length or shorter than W.
Yeah.
The system replans at most every H time steps.
So every H steps, it stops, looks ahead W steps, and figures out the next moves.
Pretty much.
Yeah.
It updates where everyone is, assigns any new goals that have come in, and calculates collision-free paths. But crucially, only guarantees they're safe for that W duration.
It's like course correction on the fly, but with a limited look ahead.
Exactly. It keeps the planning computationally tractable.
So within these windows, what are the agents actually trying to do? Just avoid crashes?
Avoiding crashes is key, but they also have goals, sequences of locations to visit, maybe. And RHCR is clever about assigning new tasks.
How so?
Well, it keeps giving an agent new goals until the estimated time to complete all its current and new tasks adds up to at least that replanning period.
So agents don't finish a task and just sit there idle until the next big replan.
Precisely. It keeps them busy, keeps the flow going, minimizes downtime.
Which ties into the overall objective, right? What's RHCR trying to optimize?
The main goal is usually minimizing flow time.
Flow time.
Yeah, it's basically the sum of the arrival times for all agents at all their final destinations across their sequence of tasks.
Yeah.
You want the total time everyone spends getting things done to be as short as possible.
Okay. Minimum total time in the system. Makes sense. And how does it actually find those paths within the window? Does it use standard techniques?
It does. It adapts well-known MAPF solvers. Things like conflict-based search, CBS, enhanced CBS, ECBS, priority-based search, PBS, conflict avoidance search, CA.
So the usual suspects from MAPF research.
Yep. The key adaptation is that these solvers plan paths through the required sequence of goals, but only worry about collision freedom within that horizon W. What happens after W is, well, the next Windows problem.
Okay, here's the interesting bit then. Does just looking ahead a short distance actually work well overall? Don't you risk, like, painting yourself into a corner later on.
That's the intuitive worry, right? But the research actually shows something quite counterintuitive,
Which is?
that using this bounded horizon can often achieve similar overall throughput, meaning the rate agents complete tasks compared to planning with a much longer or even infinite horizon.
Really?
Yeah, and crucially, with significantly less computation time, they found speed-ups of like up to 6 times in some cases.
6 times faster. Wow. Why is that?
Well, think about it. In a lifelong setting where new goals pop up constantly, a super detailed long-term plan might become obsolete very quickly anyway.
Ah, because the situation changes before the plan plays out.
Exactly. So maybe focusing on the near term is just more efficient. Plan adapt often.
Okay, a 6-fold speed up is huge. But surely there's a catch. You mentioned painting yourself into a corner.
There is a potential downside, yes.
Yeah.
If you make that time horizon W too short,
Uh-oh.
you can get deadlocks. Situations where agents get stuck because their short-term plans don't account for an upcoming bottleneck they both need to get through.
Like the narrow doorway example you mentioned earlier.
Precisely. If their horizon W ends before the doorway, neither might plan to wait for the other. They just arrive and stop. Gridlock.
Yikes. So how do you avoid that if you're using short horizons?
That's where the dynamic part of the horizon can come in. The researchers proposed an idea using a potential function.
A potential function, like
Yeah.
in physics.
Sort of. It measured how much progress agents are making towards their goals within the current window W, if progress seems stalled.
Meaning they might be heading for a deadlock.
Exactly. Then the system can automatically increase W for the next planning cycle, give them a bit more foresight temporarily to resolve the potential blockage.
Okay, so it adapts the look-ahead distance based on how things are going. That's pretty smart.
It's a way to balance the efficiency of short horizons with the need to avoid getting stuck.
All right, that gives us a good handle on RHCR. Let's switch tracks now to this other idea, shared memory, and specifically SRMT. What's the inspiration there?
SRMT takes its cues, interestingly, from neuroscience, specifically the global workspace theory of consciousness.
Whoa, okay. How does that relate to robots finding paths?
The core idea is about implicit coordination. Instead of agents needing to explicitly send messages to each other, hey, I'm turning left, okay, I'll wait, they coordinate through a shared information space.
Like a common bulletin board they can all see and update?
Kind of, yeah. SRMT, Shared Recurrent Memory Transformer, extends a type of AI model called a memory transformer to work with multiple agents.
Memory transformer, right.
So each agent has its own sort of working memory. SRMT takes these individual memories, pulls them together into one collective shared memory, and then broadcasts that shared memory back out to all the agents.
Okay, so everyone contributes their local view or intention, it gets merged, and everyone sees the combined picture.
That's the essence of it. It allows them to indirectly understand what others are doing or likely to do without needing that direct, potentially complex communication step.
That sounds fundamentally different from other ways agents coordinate. How does it compare?
Well, you've got methods where agents are totally decentralized, acting only on their own local sensors, no communication at all. That can be simple, but often leads to suboptimal or conflicting actions.
Right, like bumping into each other a lot.
Then you have fully centralized methods, like RHCR could be considered, where one planner sees everything and tells everyone what to do. That can be optimal, but doesn't scale well and needs global info.
And then there are methods with explicit communication.
Yeah, decentralized agents that actively send messages. That works, but designing communication protocols can be hard, and it adds overhead. SRMT tries to find a sweet spot decentralized execution, but coordinated through this implicit shared memory layer.
Okay, you mentioned memory transformers as the base. Can you give us a quick refresher on those?
Sure. So, standard transformers are really good at processing sequences like text. Memory transformers add special memory tokens to the input.
Tokens, like placeholders.
Sort of. They act like a scratch pad, a working memory, for the transformer to store useful information from earlier in the sequence. Recurrent memory transformers, or RMTs, make this memory persistent across longer sequences or different processing chunks.
Giving it a longer-term recall.
Exactly. SRMT adapts this by having each agent contribute its own memory tokens. These get pooled into the shared space, processed, and then influence each agent's subsequent actions.
So it's like that shared whiteboard analogy. Everyone writes their key thoughts, reads the whole board, then decides their next step.
That's a pretty good way to think about it. And it's different from some related work like ATM or RATE or RRNN. Those usually focus on each agent having its own private memory SRMT is specifically about the sharing aspect.
Got it. So where did they test SRMT? What kind of environments?
They evaluated it in simulation, mainly using a setup called Partially Observable MAPF, or POMAPF.
Partially observable, meaning agents don't see everything.
Exactly. Just like a real robot, they only have a limited local view from their simulated sensors. They tested it first on a simple bottleneck task, basically two agents needing to coordinate to pass through a narrow gap.
A classic coordination challenge.
Right. And then they used a standard benchmark called Pajima, which has lots of different maps, mazes, random layouts, maps from games like Moving AI, and even a warehouse-like grids.
A more complex set of challenges then. And what were the results? Did the shared memory idea actually help?
It performed quite well, actually. On the bottleneck task, it consistently beat several standard reinforcement learning methods, especially when the reward signal was sparse, meaning the agents only got feedback very occasionally.
Which is often more realistic.
True. And it generalized surprisingly well to bottlenecks much longer than the ones it was trained on.
Good sign. What about the harder Pujima maps?
There, it was competitive with some really recent state-of-the-art algorithms, including other learning approaches, hybrid methods, mixing learning and planning, and even pure planning methods.
So it holds its own against different families of solutions.
Yes. And interestingly, for really congested environments like the warehouse maps, they found that adding a touch of traditional heuristic planning on top of SRMT, a version they called SRMT Feller or Plan, boosted performance even further.
So a hybrid approach worked best in the toughest spots. That makes sense.
It suggests the shared memory provides good coordination, but a little explicit planning can help break really tricky deadlocks or tight spots.
Okay, SRMT sounds promising, but like any research, I assume there are limitations, things it doesn't address yet.
Oh, definitely. And the researchers are clear about them. A lot of this work, including SRMT, currently makes simplifying assumptions.
Such as?
Perfect localization agents always know exactly where they are. Perfect maps, no uncertainty about the environment. Perfect actuators, actions are executed flawlessly. Perfect synchronization, everyone acts at the exact same time.
Okay, so basically the ideal simulated world, not the messy real world.
Pretty much. Also, obstacles are usually assumed to be static, not moving unpredictably. And a big one for learning-based methods like SRMT is the lack of formal guarantees.
Meaning you can't mathematically prove they'll always reach the goal or never get stuck?
Exactly. They might perform incredibly well 99.9% of the time in tests, but you don't have that absolute certainty you might get from some classical planning algorithms.
Right. Important caveats for real-world deployment. Now, that term shared memory you used for SRMT, it reminds me of how computer programs communicate. Is there a parallel there?
That's a great observation. In computer science, specifically in interprocess communication or IPC, you definitely have the concept of a shared memory model.
Right, where different programs can read and write to the same chunk of RAM.
Exactly. It's super fast for communication because there's no message copying, but it needs careful synchronization locks, semaphores, to avoid chaos, and it usually only works on a single machine.
And the alternative is message passing.
Yes. Where processes send explicit messages back and forth, it's often easier to synchronize and works across networks, but can be slower due to the overhead of sending and receiving.
So how does the shared memory in SRMT relate to the IPC shared memory? Is it the same thing?
Not quite. It's more of an analogy. The SRMT shared memory isn't a specific block of RAM that agents are directly accessing in the traditional IPC sense.
Oh, okay.
It's more of an abstract, learned representation within the neural network structure. It's an information bottleneck, if you like, where collective state information is encoded and then distributed. It functions like a shared space for coordination, but it emerges from the learning process rather than being a pre-allocated hardware resource.
Got it. So it achieves a similar effect, shared information, but through a different mechanism, a learned one.
Precisely. It's about enabling that implicit reasoning about the collective state.
Okay, let's pivot to the real world now. We've talked algorithms and simulations. One of the sources looked at actually building a pathfinding robot using ROS, the robot operating system. What happens when the rubber literally meets the road?
Things get complicated. Yeah, moving from simulation to hardware brings in a whole host of practical challenges. The paper describes a robot using, interestingly, an Xbox 360 Kinect sensor.
Kinect from the gaming console.
Yeah, for depth sensing, basically, to see the environment and map obstacles. Then it had a Raspberry Pi for the brains, running the algorithms, and an Arduino with motor drivers, specifically H-bridges, to control the wheels.
Okay, so Standard hobbyist research robot components. What kind of robot was it?
A differential drive robot. That's very common. Two wheels on the same axle, driven independently. You steer by varying the speed and direction of each wheel.
Like a little tank, yeah.
Exactly. The paper shows the kinematic model how wheel velocities translate into linear and angular motion for the robot.
So you plan a path, translate it into wheel commands, but how do you make sure the robot actually follows the commands accurately? Motors aren't perfect.
Like,
correct?
absolutely not. That's where feedback is critical. This robot used wheel encoders.
Encoders, they count wheel rotations.
Yep. They tell the system how far each wheel actually turned. This feedback goes into a closed-loop control system,
Closed loop.
meaning the controller compares the desired wheel speed or position with the actual reading from the encoder and adjusts the motor power via the H-bridge to correct any error. This helps fight against things like stochastic drift.
Stochastic drift. Sounds ominous.
It just means small, random errors in movement. Maybe one wheel slips slightly or the floor isn't perfectly level. Over time, these tiny errors add up and the robot can drift way off course without feedback control.
Okay, so the loop is command motors, encoders measure movement mode controller compares command versus actual adjust motor power.
You got it. That feedback loop is essential for reliable navigation.
And what pathfinding algorithm were they running on the Raspberry Pi? Was it something fancy like we discussed?
Actually, they implemented good old A.
Okay, the classic.
Yeah. The paper walks through the basics, the open set of nodes to explore, the closed set of nodes already visited, the cost function GN plus HHN.
Costs so far plus the heuristic estimate to the goal.
Right. And they discussed heuristics like Manhattan distance versus Euclidean distance. They even showed comparisons with simpler searches like depth first and breadth first search on grids.
An owl comes out on top, presumably.
Yes, especially on larger grids. It explores far fewer nodes, making it much more efficient, which is important when you're running on something like a Raspberry Pi.
It's really cool to see how these theoretical algorithms connect directly to controlling a physical machine, but also how much extra engineering, sensors, feedback, control loops is needed to bridge that gap.
Absolutely. The simulation might assume perfect movement, but the real world demands sensors, feedback, and robust control just to execute a planned step reliably. It highlights the difference between planning a path and actually following it.
Okay, wow. We've gone from high-level multi-agent coordination strategies like RHCR and SRMT all the way down to wheel encoders on a real robot. Quite the journey. What are the big takeaways for you?
Well, I think RHCR shows a really practical way to handle the sheer complexity of lifelong MAPF, breaking it down using that bounded horizon. It seems effective for dynamic worlds without getting bogged down in infinite planning.
Yeah, the efficiency gains are impressive.
And then SRMT is just a really fascinating, almost bio-inspired approach. Using that learned shared memory for coordination without explicit messaging feels like it could unlock new levels of collaboration, especially as systems get larger.
But always with those trade-offs, right? RHCR's potential deadlocks if the horizon is too short, SRMT's lack of formal guarantees, and the huge implementation gap between any simulation and a working physical robot.
Exactly. There's no single silver bullet.
Mm-hmm.
The best approach depends so much on the specific context of the environment, the number of agents, the tasks, the hardware constraints, the tolerance for risk.
And that real-world robotics paper really drove home how much engineering goes into just making the basic movement reliable, even before you get to the complex multi-agent coordination part.
Totally. Path execution is its own complex problem.
So, thinking beyond just pathfinding robots, this is maybe a final thought for you, the listener. How could these ideas, rolling horizons, or shared implicit memory be applied elsewhere?
That's a great question. You could imagine rolling horizon planning being useful in, say, supply chain logistics, constantly replanning routes based on real-time traffic, demand, and vehicle status.
Yeah, adapting dynamically seems key there.
And the shared memory concept, maybe in coordinating swarms of drones for environmental monitoring, or even in distributed AI systems where different modules need to work together seamlessly without heavy communication overhead.
Yeah.
Could it lead to more emergent collective intelligence?
Really interesting possibilities. It feels like coordinating autonomous systems is only going to become more important.
I think so too.
Well, if you want to explore the SRMT system in more detail, the researchers have made their code available on GitHub. We'll put a link in the description. It's definitely a space worth watching.
Absolutely. Constant innovation happening.
Thanks so much for joining us today for this deep dive into the world of multi-agent pathfinding.
My pleasure.